Hi, everybody. I'm just sitting here playing with the pen, trying to figure out how to make it stop doing things when I don't want it to. I think I got it all figured out now. So, for today's lecture, once we get started, there shouldn't be any bugs there. Today's lecture is going to be a little shorter than normal, and the reason for that is because Chapter 3 isn't really that long. I'm going to put this on the screen really quickly. And something you're going to note is, like, that's a lot of sections, Wes. That's a big fat lie. Well, it turns out in this class, as far as I'm concerned, these two sections right here that I'm scribbling at right now, we're not going to cover those. And the reason for that is because it's a lot of really detailed minutia that is not going to be super relevant for you to be successful in this class. And if there's going to be some content that I cut, that's electron configurations is what I want to cut. You're more than welcome to read those sections in the chapter, but if you do, you'll probably be like, oh my goodness, what is all this SPDF stuff? And it's bizarre and weird, and it teaches us one thing that we're going to cheat on later on anyway in Chapter 4. But the rest of it's really crucial. This is how atoms are structured. We're going to talk about like what the pieces are, what electrons and protons and neutrons do, and why all of that's important. So let me put this back up on the screen so you can see the chat. People are starting to filter in. That's good. So after we finish talking about Chapter 3, which, again, probably will take about an hour, we'll do Q&A for the rest of the time. If people have questions, I can answer them for the second hour, which probably will be like 15, 20 minutes or so, unless people have lots of questions. Other announcements. The first quiz is due tomorrow at midnight. I should say tomorrow, 11:59 p.m., really, because midnight is actually going to be Thursday. But at the very end of Wednesday, you have to have your quiz in by that time. Once I have received all the quizzes, I will then release the answers so you'll be able to see them. Quiz 2 will go up soon. I have to finish making it. I posted the lab instead, which was just something that I decided I was going to work on. And also Quiz 3 will come up shortly after that because we have covered Chapters 2 and 3. Number of questions on the quiz, it changes. I don't actually know. It is 10 points, and it is however many questions I need to get to 10 points. But the content will cover all of Chapter 1 on Quiz 1, all of Chapter 2 on Quiz 2, and all of Chapter 3 on Quiz 3. Finally, the worksheet for lab number 1, which we went over last week, is due on Thursday, by the end of Thursday, April 30th. Make sure that you know how to upload that. Make sure that you know how to get the form to begin with. I am still getting requests for editing. That is not what you need to do. You need to watch the video from Wednesday's lecture last week, and that will show you how to make your own copy, type in all the stuff, and then download it to your hard drive, which you can then upload to Canvas so that I may grade them. All right, I think that is all my announcements. Oh, actually, you know what? No, I have two more. I do need to go back and get these pages, and I hope I still have them. I don't. That's okay. So let me go to Everett Community College. So I want this link. Oops, I didn't hit enter. And then I want this link. And then I really don't see us needing the Writing Center, but I'll copy that one too. Oh, I gotta drink more water. I got an email from another faculty member, and the faculty member said that her students in her class were not using the Tutoring Center and other available resources as much as possible. So she passed around some links. Well, she passed around some things, and I found the links. So I'm going to put some links in the chat here for you. So this is all through EVCC. So this first one is the Tutoring Center link. Make sure that if you are trying to ask people for... Oops, I'll approve that. Hold on. Make sure that if you are trying to find more resources or you need more help, we do have an online tutoring center available. The people in the online tutoring area use Zoom, so you'll have to use Zoom to video conference with them. But they'll be able to assist you with any questions. We have a dedicated chemistry tutor, although I don't know if she is working during the COVID-19 issues. But we have lots of tutors, and a lot of people are saying that like the tutoring center is just like, please contact us. We need these resources are just kind of sitting here stagnant. We also have Trio. Oops, I miscapitalized some of the letters there. Trio is a resource for people who are first generation or low income students. If you are from a underrepresented community or a disadvantaged community, Trio has a bunch of support services that can help you. They can get you in touch with things like grants, scholarships, study resources, other things like that. And then finally, we have the Writing Center. The Writing Center is just in case you're taking a class. Oops, Writing Center. I messed up the link. Hold on. Writing Center, paste. There we go. The Writing Center is just in case you want help with like writing stuff for like your English 101 class or whatever. We don't really do much writing analysis in here. I do ask you to write complete sentences in the lab reports, but that's basically it. But if English isn't your first language, or if you just haven't written like anything academic for a long time, because it's been a long time since you take high school, you can always ask them to proofread your stuff, and they would be more than happy to. Okay, so that's the announcements. Let's get started. Let's talk about atoms. In Chapter 1, we talked a little bit about atoms. They're the little teeny tiny things that have a chemical identity. If you split them into further pieces, they lose that identity, and the reason for that is because splitting them would constitute breaking apart these pieces that define them, and those pieces are shown on the screen right here. First thing we want to talk about is the nucleus. The nucleus is where the majority of the matter in the atom lives. Inside the nucleus are what are called nucleons. And so protons and neutrons live in the nucleus. On the outside, in fact, let me do it this way. Let's erase this guy. We'll make him a different color. This right here... Oh, I don't know why my pen got so thick. Oh, I'm using the wrong pen, that's why. I'm using the felt tip pen. Boop. Let's try that again. This right here, and in fact, this whole kind of region that I'm circling right now, and then I'll erase because that looks messy. This is what's known as the Electron Cloud. And the Electron Cloud is where electrons live. It's a region of space that is very, 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 very large compared to the nucleus. This diagram is showing that the nucleus is like a major part of the atom, but it turns out that if I were to actually draw an actual-sized atom, well, not actual size, because I couldn't draw that, but if I were to zoom in on one, and this was the size of the electron cloud on the outside, the nucleus would be smaller than this dot that I drew. So what that means is that the majority of an atom is actually empty space, and electrons are very tiny themselves. So it's more of a domain that has charge but very little matter in it. So this picture that is shown in the in the little cartoon here is exaggerated. This is still exaggerated as I've drawn it in the corner. It's even more exaggerated than this. Now, some features about these particles in the center of the nucleus and the ones buzzing around the outside are indicated by the symbols that you've seen written over some of them. So the first thing that we want to talk about is what charge is. Charge is an entity that you've probably experienced as like electricity. So if you plug something in, the plug and the wires that connect to that plug, that connect all the way to your device, carry charge. They carry electricity. That charge moves through the wire, through your device, and then back through the other side of the wire to go back to the outlet, which it then completes the circuit by going back to the power company or wherever it goes. That charge is actually from electrons. And we have arbitrarily assigned the symbol minus to electrons. We've just called them negative. In the center of the nucleus, however, are the protons, and they have the positive charge. There is one other particle here, and that's this guy right here, the neutron. And it has no charge at all. So there are 3 components, but only 2 of them have charges. The protons are positive, and the electrons are negative. Now, those symbols and meanings we've assigned are arbitrary. We could have said that the protons have charge A, and the electrons have charge B. What matters is that they are opposite in terms of their effect. Positive charge is one thing, negative charge is the opposite of that. What those 2 charges do when they are exposed to each other follows a lot of what you've probably heard growing up about chemistry or magnets or whatever. Things that have the same charge will do something to each other. What do 2 things do with the same charge? You can type your answer in the chat when you think you know what the answer is. And then I will promptly ignore it because I am speaking to you from the future. When 2 things have the same charge, they push each other apart. And that is known as repulsion. So like charges repel. And here come the answers. And everyone's about to be betrayed. Even though their answer is correct. Now, if I have opposite charges, these 2 do different things. In fact, opposite charges will attract. So positive and negative are attracted to each other. Positive and positive repel, and negative repel. Now, there's some interesting stuff going on here. You might think to yourself, well, wait a second. Why don't the negative electrons just attract all the way to the nucleus and then fall into the center, and then just everything is one happy positive-negative family? And the answer to that is because the electrons are moving so quickly, they don't actually get sucked into the center. For the same reason that when the Earth goes around the sun, so here's the sun. There's my sun. And we've got the Earth here. Here's the Earth. And if I draw the attraction of the Earth to the sun, it's like this. Oops, that's not what it is at all. That's me zooming in. If I draw the attraction of the sun and the Earth is pulled towards the sun by gravity. And now you might think, well, okay, what happens if the Earth gets pulled all the way into the sun? Well, it would get consumed and we would all die in a fiery hellscape. But that doesn't actually happen. The sun, even though it's malicious and is trying to pull us into it, the Earth is doing something else. It's trying to move in some direction. It just wants to move in a straight line. But the end result, between these 2 forces acting on it, its own velocity of travel, and also the sun pulling on it towards it, gives us this result instead. So the end result is actually the blue line, where we orbit the sun and go in a circle. So even though there is this attraction in the middle here from gravity that should pull the Earth into the middle, the Earth goes around in a circle because it had momentum when it was formed. By the same notion, if I have something positive in the center and something negative on the outside, these 2 should attract to each other. But because my electrons have some velocity to them, the end result is that they end up traveling in a roughly spherical orbit. Now, this would be true if there was only one electron and it was isolated from any other electron. What if I had a second electron inside the atom, or even a second electron from some other atom over here? Well, this electron sees this electron, and then they end up repelling. Just like these electrons would push apart from each other. And so what ends up happening is you have this very chaotic system that doesn't follow an orbit at all. So this works for planets. Planets have very regular orbits that we can predict. That's not how you spell orbit. There we go. But electrons do not follow this regular pattern. This guy might repel from both of these and end up going this way, and then he'll get repelled and go all over the place, and his pattern may be very, very chaotic. But what do you notice about the shape that I'm curving out? It's roughly that circular region that was on the slide that I showed you. And this region is the electron cloud. So it's very important when you're thinking about atoms that the electrons don't follow a fixed trajectory. They don't go around and around and around on like a ring. What they end up doing is they're affected by the charge of everything around them. And they end up getting pushed all over the place. So much that we can't actually predict where they are. It's not possible. But what we can do is we can say, oh, they're in this region. They're in the electron cloud. And so that's what we describe as this electron cloud that you see on the cartoon there. Okay? Unfortunately, that's really hard to draw without having that whole explanation that we just had here. So when you see pictures of atoms, they tend to have these constrained rings that electrons are on. And just keep in mind that that is a cartoon and is a shorthand and is not technically correct. Now, if components with like charges repel each other, we talked about electrons repelling each other and being attracted to a nucleus, and that balance keeps the electrons in the region of the electron cloud. What about protons? Protons would repel from each other if the neutrons weren't there. It turns out that neutrons serve a very specific purpose. And that purpose is this. Neutrons act like nuclear glue. There's something called the nuclear force, and actually this isn't the weak nuclear force. I think this is wrong. I think this is actually the strong nuclear force, but I'm not 100% sure on that. That's physics, so we don't really care about it. This is more of a curiosity. What do neutrons do? They hold protons together. And so that's really all that you need to know about neutrons is, hey, they hang out, and they keep the protons from repelling, and then everything falling apart. Generally speaking, the number of protons and the number of neutrons will be roughly the same. And I'm going to underline the word roughly because that's not always true. Usually there are about the same number of neutrons or more. But because neutrons have no charge, you could stick an extra one in there and nobody's really going to notice most of the time. We're going to talk about what that means when we talk about isotopes later on. Now, if we are looking at something at the atomic level and we notice that the number of protons and the number of electrons are the same in quantity. So if protons and electrons have the same number, then what we are looking at is called an atom. Okay? Atoms have, by definition, zero net charge. They are electrically neutral. However, if we were to change the number of protons or electrons somehow, and it's much easier to change electrons. So maybe, for example, I excited this electron and it disappeared. If I do that, we end up with what's called an ion. So if we have a different number of protons and electrons, we get what's called an ion. We're going to talk about ions a lot in Chapter 4. In fact, all of Chapter 4 is going to be based on what is ionic matter, because ionic matter is extremely common around you and the things that you interact with. For example, in table salt is ionic matter. Water has ions dissolved in it, especially if you're drinking tap water. Turns out neutral atoms, generally speaking, are rather rare. We don't engage much with neutral stuff other than things like oxygen in the air and nitrogen in the air. Air is very oftentimes neutral, but a lot of solutions and then also food that we consume and medication that we take has ionic charges. And that has to do with the properties of water, which we'll talk about a lot later too. All right. Here's the homework practice for this first little section. I want to say that the Chapter 3 slides have the correct homework practice numbers. I still need to go over and look through those and then upload all those slides. I've just been saddled down with things to do. In fact, while I'm saying that, let me write that. I have this to-do sheet. So Chem 121. Check Chapter 1 through 3 slides for homework consistency. All right, now that I've written it down, I will actually do it. Because I have a memory like sand falling through a sieve. All right, so that's the basics of what the atom is going to be constituted from. We're going to explore each of these pieces in a little bit more detail. Question, is an electron not a nucleon? An electron is not a nucleon because it does not reside in the nucleus. Electrons are just electrons. They hang out on the outside. How do we define an atom? What property tells us something about it that is consistent and that we can tabulate? And the answer is, well, we have to go to the periodic table and look at what we have assigned to each atom, and then assign that number to a feature of the atom that is essentially immutable, something that we can't change easily. And it turns out that the thing that we've chosen to define an atom by is this. It's called the... Oh, wow. Okay. I think I need to turn my pad a little bit sideways because I'm trying to draw straight lines and it's not working. We define an element by its atomic number. The atomic number is the big number that is in the top area of the periodic table box. Now, if you go to the periodic table, and let me post a link to a periodic table for you. Periodic table. All right. So p-table is a really good link. If you copy that into your browser and open up a new window, you'll see the periodic table in its entirety. And you'll notice that at the very top of the box... Oops, let me approve that too. At the very top of the box is an integer number. For example, carbon has 6, and oxygen has 8, and iron has 26, and so on. That atomic number corresponds to this feature of the atom, the number of protons it has. Now, it's very hard to... Oops. It's very hard to change the number of protons in an atom. The reason for that is because the protons are stuck together with the neutrons so firmly that we can't really do much about that. There are ways to do that. However, it is beyond the scope of chemistry. That goes into what's known as nuclear physics. So, generally speaking, atoms remain stable and their proton count does not change. That makes it easy to name stuff that way. So the number of protons becomes its identity. In this picture above here, if I had an atom with 53 protons, by definition, it is iodine. If I had something that had 36 protons, it is krypton, and so on and so forth. So now you know the number of protons in any atom based on the symbol on the periodic table and its atomic number. And we've chosen a name and an identity for up to 118 atoms so far. There are lots of atoms out there. Here's some more examples. All carbons, by definition, must have 6 protons. If you lost a proton somehow, it is no longer carbon. It would now be boron, because that would be element number 5. All sulfurs have 16 protons. If you added a proton to it somehow, It would no longer be sulfur. It would then be chlorine, which has 17. On this slide, we have some notations that we're going to use to abbreviate these terms. So the atomic number that we just talked about, which is the number of protons, we're going to call it this, Z, or if you're Canadian like me, we call it Z. Z is the number of protons. The second thing we're going to consider is this new thing. This is called the mass number. The mass number is protons and neutrons added together. It is a total count. We're going to assign that the variable A. And the reason that I'm assigning these variables here, Z and A, is because we are then going to write atoms using a notation, which is on the next slide, but I'll show it to you here. Here's my Z, here's my A. And then this capital E is going to be the atomic symbol, like a C for carbon, or a W for tungsten, or an O for oxygen, or whatever, to notate all the properties of an atom. Now remember that if you have a neutral atom, the number of protons and electrons have to be equal. The total charge must be 0. So if you know Z for an atom, you also know the number of electrons that atom has if it is neutral. If it is an ion, Z will differ from the number of electrons, and you need to use the charge to infer something about that. More on that in a little bit. Now, importantly, this number right here, A, is not on the periodic table. So the mass number is not the same as the atomic mass in the periodic table. So if I go back to the previous slide here, you'll notice that these numbers at the bottom here, so like right here, this 118.71, so these are atomic masses. But they're not equal to A. A is simply a count of how many protons and neutrons you have. And it's called the mass number because it counts the things that have the most mass. But those numbers shown on the periodic table are weighted averages for all isotopes, which we're going to talk about in a little bit. We're going to do a calculation as a sample. All right. Let's show that isotopic notation here. So here's how we'll identify a bunch of atoms in this class and beyond. So, first of all, let's see here. First thing we want to do is we want to write the atomic number. So we're going to start with Z. Oh, sorry, we got to replace this symbol. Okay. I have two versions of this slide. So we're going to look up the atomic symbol of our atom that we're going to work with. And it's going to go where this curly brackets E is. You're going to, instead of writing anything that you've seen here, you're just going to replace that with whatever it is. Don't have curly brackets in your answer. You just need the symbol. So for example, if I had like chromium, I would replace that curly brackets E with the letters capital C and lowercase r. Then what I'm going to do is I'm going to put my atomic number as a subscript, and it goes in front of E. So that's right here. We're going to put it right here. That's where we're going to put Z. Now, something important to note is that Z and the symbol are always linked, because remember, Z is the number of protons, which is going to tell you which atom you're looking at. So an example would be if I had carbon, I have to put a 6 down here because carbon always has 6 protons, and I have to write its symbol as C. Once you know the atomic number Z, you can then write the mass number A. That goes as a superscript before the symbol. And then once you have all of that, then you can celebrate because you're all done. So what this is called complete chemical symbol notation. I call it ZAE symbol notation right here, just because I don't want to type out that over and over and over and over and over. You will notice that I can't format a subscript and a superscript in the same spot when I'm doing text, so The correct way to write these is to do it this way, where they are vertically over each other. But when I'm typing and I'm limited by word processor limitations, I had to do it this way. So let me erase some of the stuff that is in the way here. And let's suppose that I had a carbon atom that had 6 protons and 6 neutrons, and I wanted to write its ZAE symbol. Well, I know that carbon has 6 protons because that's definition. It must be carbon if it has 6 protons. And then up here in this space on the top would go the mass number. I need the mass number, which is protons plus neutrons. 6 plus 6 is 12. I put 12 there. And there you go. That's the answer. So on the screen here, I have several different atoms that I want you to try and write the isotopic notation symbol for. So based on these descriptions and the clues that I've given you, and be careful because I've sort of made it like a puzzle. So look carefully at the information that's available and then write out the ZAE symbol. And then at the bottom here, I have 3 questions that I want to ask you about various atoms. I want you to count the pieces that are in there. When you're done with that, I think I have another slide coming up. Maybe it's not just yet, but there'll be a table that we fill in with all this information later. Okay, so go ahead, take 5 minutes to fill in this information, create these symbols, answer the questions. We'll go over the answers in just a second. All right. So hopefully we've had enough time to go over the answers here. I'm trying to think of a good way to write all of these in here. So let's go back here. Oh, do we need more time? Should I put this back up? I'll give you three or so more minutes. That's fine. We have all day for chapter 3, and we're already like halfway done. So I'll give you 3 more minutes. Go ahead and work on it, and I'll be back in just a second. I'll go fill my water. All right. Let's go over the answers by clicking on this. I stole my sun up here because I didn't erase it. Oops. Select all. Goodbye. Oh, I erased the wrong layer. Hold on. Everything is ruined. Boop. Boop. There you go. Okay. All right, so for this first one, I want to describe an atom of chlorine with 16 neutrons. So first of all, it's chlorine, so I'm going to look at my periodic table. I got to find chlorine on there. It's somewhere. And it turns out that it is the element Cl. That's a lowercase l, by the way. And its atomic number is 17. So I would write this here, 17, 1, 7. Now I have to incorporate the neutrons. Now remember that if Z is 17, A is going to be protons plus neutrons. And so that's going to be the 17 for my Z and 16, which the question has prompted us. So A for this atom is 33. And this would be the notation for the first atom, 1733 Cl. For the second one, I gave you the information by just telling you what Z and A were outright. So here's Z and here's A. But now we got to go look up what element this is. We do that by using Z, which is 25. So I got to find the element with atomic number 25. And that's manganese. So that's this element right here, and you're all set. For the third one is my challenge problem here. So hopefully you got this. I need to have an atom that has the same number of protons and neutrons, and A is 36. So I know that A equals 36. And I know that that is equal to the number of protons and the number of neutrons. But I also know that the number of protons and the number of neutrons for this specific example are equal to each other. So what that means is that this guy has to be half, and this guy has to be half. So what number times 2 makes 36? Well, there's only one number, and that's 18. So now that you know that, you can say, well, Z is 18, A is 36, because the problem told us. And let's go find element 18 on the periodic table. That is argon. And that's the answer. Finally, we've got these questions that ask about the specific isotopes and how many components they have. For the first one, how many protons does silicon-28 have? Well, by definition, all silicon must have 14 protons. And that's shown right there. How many neutrons does potassium-39 have? So if I have 1939K, the number of neutrons is in this number somehow. But remember that this is the number of protons. Oops, I messed up there. So protons plus neutrons. And this right here is protons. So if I did A minus Z, I would get the number of neutrons. So that means 39 minus 19 must be 20 neutrons. And then finally, how many electrons does this sodium atom have? Is it 20? It's 24, okay. How many electrons does this have? Well, again, this is protons. This is protons plus neutrons. Nothing in here tells us anything about electrons. But remember that for a neutral atom, the number of protons is equal to the number of electrons. So we would say that this has 11 electrons in it. Now, I am making an assumption that it is a neutral atom. All of these were intended to be neutral atoms. We haven't talked about ions yet. Okay. All right, so those were the questions. Let me put the homework practice back on the board once I get this clicked on. There we go. I believe that's the end of this section, although we had to talk about isotopes a little bit. So let's see here. Let's take our break right now, I think, because I'll try and split it down the middle of like how much content we have left. I'll put the title card up. We'll put the break time timer up. I do still have live split on, so hopefully it will find it. There it is. Oh, I gotta reset the timer. How do I do that? There we go. All right, so we'll start the 10-minute timer, take a break, we'll see you in a bit. Oh, I was really, really close to stopping that on exactly 10. One of these days. All right, so there's been some discussion in the chat. There was a Discord server being passed around, or some contact information or something like that. As somebody who uses a lot of Discord, I can say that it is very, very useful in communication. You can put it on your phone. I would highly recommend it. I would love to join it, except I think that that would probably be a conflict of interest for various reasons, unfortunately. So I can't join your server. But if you have questions for me that your group comes up with in there, please put them on the discussion board or email me. It's a great resource, so make sure to use it if you have that available. Let's talk about isotopes. So, isotopes are a combination of protons and electrons and neutrons. Now, if I have... Oh no, I said please. I said Discord. Now everyone wants me to join. I don't know if I legally can. That's the thing. So Discord is a chat service. It's kind of like... Gosh, I don't even know any modern equivalents. Skype, I guess, would be the most modern equivalent. I almost said AOL Instant Messenger, just to let you know how old I am. It's like that. It's like ICQ, MIRC. God, now I'm just dating myself. Skype is probably the most modern version that is out there. But it's kind of like what the chat log looks like right now. You type in something, and then it's a log that's there forever. You do have to download an app if you want to make an account, although I think you can join using the web browser. I don't actually do that. I just have Discord on my phone and on my computer. I use it for various stuff, so I have groups that I talk to. I play video games with friends, and we use that to chat. But again, I don't know if it's like legal for me to join your group for that purpose, because like it's a whole can of worms that like I have to worry about, like engaging with students beyond the scope of the classroom. So I don't think that that's something I can do, like ethically. It's appropriate. Let's get back to the lecture. So if I am looking at sets of atoms, I think this is going to put a bunch of borons on the board. There we go. Okay. If I'm looking at this and I am counting the number of protons and the number of electrons, and then I'll also count the number of neutrons. And so what I would notice is that because all of these are boron, they all must have 5 protons. So we'll just write that in there. There we go. 5, 5, 5. Now, if I'm going to count electrons, because these are electrically neutral because they're atoms, though I turned my thing a little bit, sorry, then these all have 5 electrons as well. So no surprises there. But if I were to look at the mass numbers here, you'll notice that the mass number is changing in each of these. Since the number of protons and the number of protons plus neutrons is shown here, I can take the top number minus the bottom number, or A minus Z, to get the number of neutrons. So this must have 5 neutrons, but this one should have 6, and this one should have 7. These are all still boron, because they all contain 5 protons, but they weigh different amounts. And so what we note here is that the number of neutrons varies between boron atoms in these cases. The indication that you are dealing with isotopes is that you want to look at these numbers. Wow, I'm the worst at circling things. Hold on. Let me get rid of this. All right, we're going to circle. Ready? Circle. I circled everything. That's not useful. I will get this. There we go. I did it. What you want to look for is this phrase here. Same Z, different A. If you look at different atoms and they have the same Z but different A's between them, then what you are looking at are isotopes. Now, isotopes, by definition, have to be the same element. So you can have isotopes of boron and compare them towards each other. You can have isotopes of nitrogen and compare them towards each other. But two atoms that are different elements cannot be isotopes of each other. So something like this and this, these can't be isotopes. So isotopes are sort of like a subfamily within a family of an element. More text is going to appear under this, so I have to clear the screen so I can let it up there. And so again, number of protons and electrons will be the same within my isotopes, but the number of neutrons will vary. And there's our same Z, different A. How many isotopes naturally occur? It turns out that depending on the atom, you can have all sorts of naturally occurring isotopes. So naturally occurring isotopes are the ones that exist today. For instance, if you had an object that contained only carbon, and you were to look to see how many isotopes that are in that sample, you would find 2 or 3. If you had something like tin, like the metal tin, and you looked at how many isotopes were in that sample, you'd find like 10 of them. There's tons of tin isotopes. Some elements only have one isotope, and some elements don't have any that are stable at all. Now, any combination of protons and neutrons is possible, and this is what's called a synthetic isotope. If you have an isotope that isn't a stable combination, then what ends up happening is it decays. And this is actually known as radioactivity. So if you have an unstable atom, because the number of protons and neutrons isn't the right ratio, for example, not close to that 1-to-1 that I said before, then the atom falls apart on its own. It tries to stick together for as long as it can, and then it just explodes into bits and pieces. It's like a bomb, basically, going on. Those elements are radioactive, and so synthetic isotopes are things that you generally prepare and are generally radioactive. In the medical profession, an important isotope is something called fluorine-17. What fluorine-17 is used for is positron emission tomography, and it's used for medical imaging. Other important isotopes, there's isotopes of barium that emit gamma rays. That allows you to take X-rays with them and to identify, like, say, if you drink barium, or the barium solution. I've never actually drank it, but I've been told it tastes really terrible. What it does is it highlights all of your intestines, and so when you go get X-rayed, the barium emits gamma rays, which are then detected by the device, and then you can image organs that you would normally not be able to use just regular X-rays to do. So isotopes have a lot of interesting properties, and it's good to know what they are in case you're working with them. For this next section, what we're going to talk about is how we determine the mass of atoms, and also what that mass on the periodic table means. On the board here, I have the mass of a carbon-12 atom in grams. That is a really obnoxious number to deal with. So what we're going to do is we're going to create a new unit, and we're just going to say that weighs some number of this unit. And so the unit we're going to use is called the AMU, the Atomic Mass Unit. Wow, I don't know what is... I am the worst at drawing lines today, I'm sorry. There we go. So the abbreviation for that is AMU. And for our purposes in this class, one AMU is the mass of either one proton or one neutron. So for instance, in the page before where we were trying to figure out boron-12, for example, the mass of boron-12 would be 12 AMU. Now, because electrons are really tiny, and you need tons and tons of them to get to 1 AMU, we round down. We just say that they weigh essentially 0 AMU. Now, in reality, the numbers are not as exact as this. For carbon-12, it is 12 AMU because there are 6 protons and 6 neutrons. But for all other atoms, there's a little bit of a deviation. We're going to ignore that deviation, and we're going to just round for our purposes. If you're interested, this is how those numbers are obtained. For instance, carbon-12 is exactly 12 AMU, and we just chose that as our benchmark. And then using a precise device known as a mass spectrometer, we can weigh stuff. And the way that that works is, basically, it's like launching atoms over a catapult. And I'll draw a picture to show kind of what's happening here. So if I have my atom right here, and we'll say it's carbon-12, and I fling it, it'll go a certain distance based on how much it weighs. And so I know anything that lands here has to weigh 12 AMU. Well, now what I'm going to do is I'm going to throw something different. I'm going to throw something that's a little bit lighter. And because it's lighter, if I use the same force, it ends up going a little bit further. Now, because I have a scale now, what I can do is I can say, oh, okay, where did this land relative to this? And we'll give it a weight. And I can do that with any atom. So if I weighed something that was heavier, then it just wouldn't go as far. And so we're basically launching these atoms through this device, and the device is called a mass spec. And what the mass spectrometer does is it detects when things collide with its detector based on how strong the field strength is of the magnet that we use to bend atoms through it. And there's a lot more details than that, but I'm just going to hand wave that because that's beyond the scope of this class. But by using this sort of technique, we can get really precise numbers. And it turns out that when we do these sorts of measurements, we end up getting a number that isn't exactly what we would expect it to. So for boron 10, you would say, oh, it should weigh about 10 AMU. And it turns out that it does. It's just that we have these extra digits on the end. For our purposes, we're going to just round. So if I ask you on a quiz or assessment, and it will say, give a rounded answer, and I say, what is the mass of boron 10 in AMU? You would say 10. Now, this mass right here, boron 10, which I've reported as 10.013, this is known as the isotopic mass. This is the mass of this specific isotope. So boron 10 is 10 AMU. And I had too many wiggles for that letter there. Uh-oh. Now, here's a question for you. What if I just wanted the mass of boron? And so that would be all boron. Now, boron would be a collection of boron 10, boron 11, boron 12, etc. So depending on what you grabbed, you'd get a different weight. It'd be 10, 11, or 12. But we don't grab individual atoms. What we end up grabbing are just handfuls of things. And if I wanted to know on average what they weighed, it would depend on what I grabbed. For example, let's suppose, we'll go back to the power, or this guy here. Let's suppose that I had a bag of marbles. And so, like, I have red marbles in the bag. I got a bunch of red marbles in there. And I also have blue marbles. Alright, so there's my marbles. And I know that by measuring them using my mass spectrometer, the blue ones weigh 5 grams. And the red ones weigh 7 grams. Now what I'm going to do is I'm going to reach in and I'm just going to grab a handful of marbles randomly. I grabbed these guys. What is the average weight of the marbles? Well, it's going to depend on which ones I grabbed and how many there are. If there are mostly blue, I'm going to get a mass that's close to 5. If they're mostly red, it's going to be a mass close to 7. If I have 50-50, it's going to be somewhere in between. Now, if my matter looks like this, I drew 5 of each, so any random grab that I get, I will probably get about half blue and half red. But what if my sample actually looked like this, and there were far more blue marbles than there were red marbles? Then my average would be much closer to 5. In this way, we can actually calculate the average mass of atoms by knowing how abundant they are. And this has been done for you. If you go to the periodic table, and you go back to the first slide, so we're going to go all the way back to this slide right here, and you see these numbers right here that I've circled, the atomic masses. So here's some for these elements right here. These atomic masses are the average of all naturally occurring isotopes in AMU. So what that means is that if I have gallium, and you can see there that it says gallium is 69.732, and I asked you which one of these is more common, 69 gallium or 70 gallium? Which one must be more abundant? And the answer would be this one. And the reason for that is because the average is closer to 70 than 69. We can do the same thing over here for selenium. Which one is more abundant? Selenium, which is 77 mass number, 78, or 79, which I messed up writing there. And you would say, okay, which of these numbers is closest to the average mass? And that's this one. So therefore, selenium-79 must be the most abundant. And this will work 99% of the time. There are some elements out there which love to be jokes, and one of them is actually right here. I'm going to put this one in red. So sometimes this doesn't work. We're going to look at bromine. And you might ask yourself, which is the most common? 79, 80, or 81? Oh my goodness, I'm not writing on the right thing. I'm so sorry. I did not click on the right thing. I apologize. Let me go back and do this again. We'll just erase all. I'm so sorry. So looking at these numbers right here, these are our atomic masses on the periodic table. And what the atomic masses are, these are the average of all naturally occurring isotopes. So I'm all the way back a bunch of slides, so we were very far forward. I scrolled back to get to this periodic table to show this. So in case you're looking through your slides like, where did he go? That's not the next slide. Yeah, we went back about 10 or 15 slides. Now, based on these masses that are shown on the periodic table, you can make some assumptions about what isotopes are abundant and which ones are not. So for example, if I was to look at gallium here, gallium has an average mass of 69.732. So I'm going to write that up here. Now from that, I could conclude that there must be more of some isotopes than the other, because otherwise it would be exactly the same number, 69 or 70 or whatever, or it'd be like 69.5 because it landed in the middle. So of these two isotopes, which one would be the most abundant? Gallium-69 or gallium-70? And because the average is closer to 70, this one must be the more abundant one. I can do the same thing with selenium here. For selenium, I could say, is it selenium-78 or selenium-79? Or even selenium-80? And I'd say, well, because the average is closest to 79, this one must be the most abundant. And 99% of the time this works. There are some instances, however, when it doesn't. So let me change color here. Right here, this guy right here. Here are 3 isotopes of bromine. And if I asked you which one was most abundant, you would immediately follow the pattern that we just did and say, well, 79.9 is closest to 80, so bromine 80 must be the most abundant. And you would be absolutely 100% wrong. And the reason for that is because the actual statistical breakdown of what there is for bromine is there are half and half bromine 79 and 81 and absolutely no bromine 80 for some reason. So this is nature just going, haha, suckers, all these patterns, and I'm going to ruin them. So, I mean, just unfortunately the patterns don't always work. I won't give you examples that are like that. I will stick to the ones that will be accurately predicted by this model, so like the selenium example and the germanium and the gallium, etc. I won't pick the bromine or the chlorine where the answer is weird. But yeah, that's just nature. Nature's like, hey, there's no bromine 80. It's half and half 79 and 81. And that's just a coincidence. I'm going to scroll back to the slide that we are on, which is right here. And so that's why I brought this up, because this next slide tells us that this is actually a thing that occurs. So let's suppose that half of the bromine in the world is bromine 79, and the other half is bromine 81. What would the atomic mass be? And we can figure that out by taking the average of those masses and then calculating it. And we get an answer that would be approximately 80. And you can see on the periodic table that it's 79.90. This is close enough for our purposes. 1, because these percentages are not actually 50 and 50. And 2, because these numbers are not exactly 79 and 81. There's a little bit of error here, and we're just rounding it away so that we don't have to deal with it. So all of these atomic masses have been calculated, and you will not need to do that calculation in this class. You just need to refer to the periodic table to get that number for whatever application you need it for, which we will be using it later on in Chapter 6. Okay? So, important things to note. You will need to know that the atomic mass is what's on the periodic table, and that the isotopic mass or mass number refer to individual isotopes or the letter A for the variable that we have. All right. This first problem is just a sample, like, how do I get the atomic mass of something with different percentages? Don't actually do the first problem. I will do it for you just to show you how average masses are calculated. But the second question is what I want you to answer. So the atomic mass of chlorine is 35.453. There are only 2 isotopes. Which is there more of, 35 or 36? And then how many of the atoms have the mass exactly 35.453? And I have this in the parentheses for a reason. Okay? So go ahead and answer those questions. I'll go over the answers in about 3 or 4 minutes. Good luck. All right, I hope you've taken a second to think about those questions. What I'm going to do now is I'm going to leave that diagram actually on the screen because I want to use it later. That's not the one that I want. I want to make it bigger. There we go. Actually, I guess I can't make it that much bigger. All right, so for this second problem, we'll go over this first problem in just a moment. The atomic mass of chlorine is 35.453 AMU. There are only two isotopes, so there's chlorine-35 and chlorine-36. For this example, it turns out that chlorine-36 doesn't exist. But of these two isotopes, which is there more of? Chlorine-35 or chlorine-36? Well, you would look at the number and say, okay, 35.453 is closer to chlorine-35, so this must be the more abundant one. And it turns out that that's correct. Now, the second question asks you, which percent of atoms have a mass of exactly 35.453? And you might be looking at those percentages and saying to yourself, well, oops, hold on. That's what I want to do. I want to get rid of that. Wait a second, what does the percentage tell me? Maybe 45% of them are chlorine-35 and the others are 36. Well, let's put it this way. We'll say that the blue ones are chlorine-35 and they weigh how much? Well, if it's chlorine-35, it weighs 35 AMU. My pen just died. That's weird. Oh, I know why. I'm in a selection. Hold on. Okay. There we go. And then we'll call the red ones chlorine-36, which there are less of. And if I took a random sample, which would be this guy, then the average mass would be what we calculated on the periodic table. But the question that I'm asking is, what percent of these atoms, and these are my atoms here, what percent weigh 35.453? And if you're thinking to yourself, well, none of them weigh 35.453, and also I wrote off of the part that you can see here. None of them weigh 35.453. All of them weigh either 35 or 36, and that's correct. So the percentage of atoms that have this mass is none. And so some people might look at that and say, that sounds like a trick question, Wes. And I'll say, there are no trick questions. If you know what atoms and mass weights are, that's not a trick question. That's an easy question. But it tricks you into making an assumption. And that's where the trick comes in. So the trick is to see through that. So whenever you look at the periodic table and look at the mass of an atom underneath, remember that that atomic mass is not the mass of any individual atom. That is the average of all the isotopes in a random collection. That is an important distinction to make. Oh, good. If you said that it was 0, then that's awesome. I'm happy if people thought it was 0. That's a question that we ask every time in Chem 121, and a lot of people struggle with that one. All right, so let me do this. So we discovered this new atom X, which is totally bogus. We did not, but that's okay. So we know that this isotope of X is 20% abundant, so there's 20% of it there. And this isotope of X is 80%. So what we need are the mass and the abundance, and I have the abundances right here. So we know that something that has a mass number of 43 is going to weigh about 43 AMU, and something that has a massive number of 44 is going to weigh about 44 AMU. Now, how do I take an average when I don't have the same amount of things? And the answer is, well, how do you take the average of anything? And the formula that we teach you is that, say we wanted to take the average of these two numbers. You'd add them together and divide by 2, right? That's the same as saying that I'm going to multiply each of the numbers by half. And what we've done is this is our weight. These are what our weights are. So we have weighted each of these numbers to be the same. They have the same impact. But let's suppose that instead of having 1 over 2, I said, okay, this one's 1 over 5, and this one's 4 over 5. More of it is going to be this atom than this atom. Now my calculation changes slightly. In fact, if I punch this into my calculator, then the answer that I get is 5.8, which is closer to 6, and that makes sense because there's more things that weigh 6. So we can do the same thing up here. I just turn these into decimals or fractions, and then times them by the numbers that they're associated with. So I would say 0.2 of my stuff, because that's 20 over 100, or 20%, times 43, plus 0.80, because that's 80 over 100, or 80%, times 44. And then I would multiply those numbers together. And punch them in. And when I do that, the number that I get is this. I'm going to assume that these are all exact numbers just for this example. But this is how we get numbers for average masses on the periodic table. All right, there's the homework practice. I thought this was going to go a lot faster than it actually is, so we will finish the chapter. There's just 2 very brief sections left. You will need the periodic table handy for this. So if you haven't gone to, it's even called the periodic table, so if you haven't gone to ptable.com, open up a copy of the periodic table right now. I'll give you a second to do that. And what we're going to talk about are various features in the periodic table that we're going to refer to by name and context, so that when I say, oh, we're going to call this element group 4, you'll know what that means, and we can shorthand and refer to stuff like that. First thing I have is a demo. I think we've already done this demo. Did I show everybody the demo where the elements explode, where you put like sodium and water, and it fizzes and pops and blows up? Did we see that? Oh, we haven't done that. We have not seen sodium blowing up. Oh, well, we're in for a treat today. Okay, so hold on. Let me get my cursor. Okay, so the first thing that I have to do is I have to capture the window. That's live split. That's not useful. All right, so I got the window. I have to reveal the window, but I don't... Where is the window? There it is. Okay. There's all of my music that I've been streaming you guys on the side there. We'll get rid of that. All right, so what you see here, this is a thing of water. And what we're going to do is we're going to put sodium in it. Let me make sure that we have audio here because we want to actually hear the sound that this makes. Okay, so on the screen right here, this is my sodium metal. We're going to put it in the water. Here's what happens. All right. So sodium metal, the like elemental neutral metal with 11 electrons, 11 protons, is very reactive with water. If you drop it in, it lights on fire. Now the next thing that we're going to do is we are going to, I got to make sure that I get to his page here. We're going to look at different elements and see what they do in water. And it turns out that this guy has done a lot of elements in water. So we're going to look at potassium in water. All right, so here's potassium in water. Here we go. And I'll give you a second to respond to this. What did you notice about these two experiments? Like, were they exactly the same? Were they different? Were they similar? Were they not at all alike? Like, what would you use to describe them? I'll play it again for you. So here's potassium again. Go ahead and type your answers in the chat now. And then we'll go to sodium and water again. So what conclusions can you draw about these two elements? Are they alike, identical, similar, different, or wildly different? While you're typing in your answer to that question, I'm going to get the next metal here. So the sodium one was more chill. The potassium one bounced around. But they did both catch fire. That's interesting. Now, the next element that I'm going to show you is rubidium, which is Rb on the periodic table. If you have your periodic table handy, have you figured out which elements I'm picking and where they are? So here's rubidium. We're going to hit play. Be careful, because if you blink, you'll miss it. All right, here we go. And here it is in slow motion with old 8-bit sound effects. All right, that was rubidium. Was that what you expected it to be? Type in your answer in the chat, and while you do that, I'm going to get the next element, which is cesium. Which you could probably already see, because I think the link out... Yeah, it's right there. All right. This one I had to wait for, because if you blink, you really will miss this one. Here's cesium. 3, 2, 1. That was it. Here it is in super slow motion. And it just explodes very quickly. Now, that was just a little bit of fun stuff about elements. But why did I show you this? And the answer is that in the 1800s, 1700s, back in those days, people were doing experiments with matter, and they were trying to figure out various properties that were consistent. And what people discovered was that, certain elements explode when I put them in water. But what they noticed about this was that they started to form sort of patterns. So if I take my periodic table here... Oops, I got to click on this. There you go. And instead of having a periodic table, I just say this. We have the periodic line. We'll just do that. Here's my periodic line of elements, because the periodic table didn't exist all the way back then. Instead, what we had was just a bunch of elements with a bunch of numbers associated with them, and no real rhyme or reason what this meant. What people noticed was that certain elements were explosive when they were put in water. So 11, 19, 37, and 55. Now, that on its own is not super exciting. But what was particularly notable was that when people looked at the elements before these, they also found a pattern. And this pattern was that these elements were inert, what you may have heard of as the noble gases. And so people saw this and they thought, that's interesting. Maybe there are more patterns. And as it turns out, there are tons of patterns on the periodic table. So what a scientist did, his name was Dmitri Mendeleev, and I think I have a picture of him on the next slide, is that he arranged, oops, I clicked on the title card. He arranged all of the elements by group. And so elements that are in the same column have similar properties. They behave in the same or similar ways. So to show that, let's go back here, and I want you to predict, before I actually get the video on screen, like type it in the chat or think of it to yourself. We're going to pick lithium. Lithium is on the periodic table right above sodium. Based on what you've seen and what patterns you have observed, tell me what lithium will do and about how excitedly it will be. Okay? So make your prediction. We'll type in lithium. And here it is. Spoiler. It's probably what you thought. Here we go. Here's lithium and water. All right. So did it match your prediction? Hopefully you predicted that it would still react with water because it's in the first column with all these other elements that react with water. But based on where it is relative to the other ones, they seem to be getting more reactive as we went down. Maybe this one would be less reactive as we went up, and sure enough, it was less reactive. The next thing we're going to do is we're going to do calcium and water. Calcium, you'll notice, is not in period 1, or in group 1, sorry. It's in the second column. It's right next to potassium, number 20. This is what calcium metal looks like. This is elemental calcium. It looks very different than the calcium you're probably used to thinking of when you think of milk or cheese or bones or whatever. That's because this calcium has the same number of protons and electrons, and that calcium in milk and things like that is an ion. It's different. It makes a precipitate that's white. We're going to put it in water, and based on what you've seen and where it is on the periodic table, do you expect it to explode when we put it in water or not? Well, here we go. Let's see what happens. That explosion any day now? Well, I think it's just going to sit there and kind of fizz. But you can actually see the white in the water from the calcium ion dissolving and making a precipitate. The calcium metal is turning into calcium ion by reacting with the water. But what we would note here is that that reaction was a lot different. That didn't look anything like the exploding stuff that we saw before. For one, it didn't burn, it just sort of bubbled. And the reason for that is that it is in a different column, and so it must behave differently than the elements in the first column. So this guy, here he is, Dmitri Mendeleev, he realized that there were these patterns on the periodic table, and what he did was he arranged the elements into the first periodic table, which you can actually look up online. You can look up at Mendeleev's periodic table. It looks like a giant square. It's not as long, but it organized elements based on their properties. And from there, we refined it to what we have today. Now, very interestingly, is that in the time that Mendeleev was doing this research, there were certain elements that had not been discovered yet. For example, I believe gallium and germanium had not been discovered yet. They were just blank spaces. Like, there was no element 31 and 32. So what he did was he said, I'm going to predict that this element will be similar to, and so like, for example, gallium. It's going to be similar to aluminum and indium. It's going to have a melting point between the two, and it should make this type of ionic compound. And based on all the predictions he made, they were able to identify gallium and put it on the periodic table, and he was totally right about all of them. So this periodic table is very, very, very good at predicting stuff. And there are 110 elements. I want you to memorize them all. No, I'm just kidding. So you do not need to memorize the elements. Instead, you will always have the periodic table handy. We have since filled in the blanks in these spaces, so we know all the way up to element 118. Those have been discovered. Those discoveries were fairly recent in the grand scheme of things, like after 2000. I just happened to put this picture up there when I made the slide, and it was an old picture. But these elements are arranged in different coordinates. We've got the up-down coordinate and then the left-right coordinate. We're going to talk about what those coordinates mean. So the first coordinate we're going to call is the group. Groups go up and down. And we'll highlight the word column. We number groups left to right, just 1, 2, 3, 4, all the way up to 18. Now, there are two different notations for groups. So you may have a periodic table that has like 1 through 8a and 1 through 8b, or your periodic table might just list 1 through 18. We'll use both. We'll talk about that a little bit later. Elements that are arranged in the same group will react similarly to each other. Elements in different groups behave differently. We have arranged the periodic table so that it follows that pattern. Going across the table is what's known as a period. This is where the word periodic in periodic table comes from. These patterns occur periodically. Every time you go down to the new row, you see the pattern emerge again. So period 1 is the first row, period 2 is the second row, period 3, and so on and so forth. The period number is not going to be super useful for us in this class, but it does have some information later on that we'll talk about. On the screen here are various group names that I want you to know. So the first group name that I want you to know is that group 1A is the alkali metals. And that's a common enough name that we're going to run into that all the time. So we might say alkali metals are reactive with water. So that means everything in this column. The second column is also common enough. These are the alkaline earth metals. So that's column 2A. Other columns that I want you to know, over here, we want to know where the noble gases are. That's 8A. Elements in column 8A are inert. Like all nobility, they sit on their asses and do nothing. These substances just don't react. They don't do anything. And there's a reason for that, which we'll discuss in chapter 4. Halogens are in column 7A. Halogens are extremely reactive. This blank box right here, I actually don't know why this periodic table is doing that. Ignore this box right here, and this guy should go home over to 1A because that's where he lives. Ignore this zigzag line here. The other thing I want you to ignore is chalcogens. Nobody gives a shit about chalcogens unless you work in a chalcogen lab. Any chemists out there who've stumbled upon my video, chalcogens are silly. Sorry. They're just not important enough to give a name. Same as this column number 5. It doesn't even have a name on this chart. They're called pnictogens. That is also silly. Those are not common enough that we need to use those names. But these other names are common enough that we care about them. So I do want you to know about alkali metals, alkaline earth metals, halogens, and noble gases, and what column they are in. You'll note that my columns are labeled 1 through 8A here. If I were to number them just across, then they would be numbered like this. There you go. There is one other group of metals that I care about on this periodic table. Actually, I should label these guys down here too. This group right here in the middle, this that I'm bordering in blue here, this group of metals is known as the transition metals. And the transition metals are basically the transition from the left side of the periodic table to the right side of the periodic table. That's why they're called that. Transition metals are very common. Some of them, like iron and copper and nickel, are things that you interact with every day. And then finally down here, this first row is called the lanthanides. And the second row is called the actinides. And together, these are called either late transition metals, or you may have heard them called rare earth metals. But they're not actually rare, there's actually tons of them, so that's kind of a bad name for them. The only reason I bring up the ones in green, those are also esoteric, so I would include them with chalcogens and pnictogens as being silly and you don't really need to know. But I personally did research on lanthanides in a laboratory, particularly this lanthanide down here. Wait a second, that's not an lanthanide, Wes. Yeah, I was in a lanthanide lab, and they gave me uranium to work with. So that tells you how much they thought of me. So I did research with all those elements. I know a lot about them, and it's interesting. So I'd like to talk about that a little bit. But the stuff that is highlighted, so this stuff up here, the stuff that's highlighted is what I mostly care about. And I guess I should highlight this one too, because this is common enough that we care. Okay, so you got to know what those names are and what groups they are assigned to. Here's my exercise for you. I want you to label the names of these elements as alkali metal, alkali earth metal, halogen, noble gas, or none. And then also tell me the period and the group number. So, referring to your periodic table, refer to these elements by those properties. Instead of writing none of the above, you are allowed to write transition metal if you'd like. I will accept that as correct. But go ahead and look these up. I'll give you 2 or 3 minutes to do it. Then we'll go over the answers. We'll talk about metals real quick, and then we'll call it a day. All right. I'm going to go over the answers because we only have like 3 minutes left. I'm not going to actually be able to do metals today. I'll just quickly do that at the start of the next time. So, looking at this first element, AT, hopefully you found it. It's in the bottom right corner, and it's called astatine. What period is astatine in? It is in period 6. And it's in group 17. You could also say 7A, that also works. And because it's in group 7A, it is a halogen. That should be an N, not an R. K is potassium. It is in period 4. It is in group 1 or 1A. Either of those is okay. And it is an alkali metal. Now, if you accidentally said alkaline metal, that would be okay. This is gold. Gold is in period, I gotta count, hold on, 3, 4, 5, 6. It is in group, I can't read the number on my periodic table, there we go, 11. Which is also 1B. And it is a transition metal. This is rhodium. If you know what a little bit of Latin, rhodium comes from the word rhodos, which is called a rose. And this is known as rose gold. So if you have rose gold jewelry, you have rhodium. And it's in period 5. Group, I think it's 10, right? 9, okay. Group 9. And I don't have another periodic table handy. I think this is also 8B. And it's also a transition metal. And then finally, this last one down here, tellurium. Tellurium is the stinkiest thing that I can think of when combined with hydrogen. Stay away, basically. It's also in period 3, 4, 5. Group 16 or 6A. And it is a chalcogen, so nobody cares. None of the above. All right, here's the homework practice for this section. I will do metals tomorrow because I don't want to keep you here for an extra 5-6 minutes just to talk about, oh, things are metallic when you move left or right. So we'll do that on, not tomorrow, but Thursday's lecture. Tomorrow is a Q&A. I will go over lab number 2 and what you need to do. Then I will answer any questions about lab number 1. And then I will answer any questions in general. Make sure that you post that Discord link on the discussion board because people will definitely use that. Discord is great. Thanks for watching. I will see you all tomorrow. I'll stick around in the chat for a few minutes for questions. Take care and have a wonderful evening. I apparently hid the wrong thing when I went back, but that's okay. Where's my music? We gotta fade out something.